so welcome to the next lecture. Talia Polini with our second lecture.
Thank you so much. So guys, I want to remind you first that you should stop me if I go too fast. Do not hesitate to stop me. It's very important. It's more important that you understand that I can cover everything. I mean, you can always study the rest in the notes I'll give you. So let me do a computation I was doing last time and was not clear. So I want to redo it to make it clear. So remember, I want to prove that, I'm still proving that this guy is with the derivation delta that we defined, and now I'm going to redefine it, is isomorphic to omega r with dri, which I call d. So I want to prove this isomorphism, and now let me remind you who this guy is. This d is the kernel of the multiplication map from the enveloping algebra to R, and this is just multiplication, okay? And this is the kernel, okay? And since I go modulo d squared, this becomes an R module. And now the map delta, this guy is generated by x tensor 1 minus 1 tensor x, okay, by these guys. And now the map, you know, delta goes, I mean, since we want it to be a differential, let me write it like this, goes from R to d over d squared. And what does it do? He sends an element x to the image, to x tensor 1 minus 1 tensor x. Okay, it's enough to find it here, and this is obviously an element here. So we already argued that d mod d squared is an R module, and we were trying, this map is defined as an R linear map, and we were trying to prove first that this map is an A derivation, okay? We already saw that since it's R linear is A linear, okay? So the only problem was the multiplication. And I did it last time, but I want to redo it now. So how do we look at the multiplication? So we have two elements, okay, in R, and you take delta of xy. And this delta of xy is xy tensor 1 minus 1 tensor xy and the image. So that's how it is. And now we put inside, as I said last time, so this is the same, x tensor y and plus x tensor y. And then we have minus 1 tensor xy. And then we close this. And this is equal, maybe I write down now. This is equal, so I want to take them together, but you have to be careful how the multiplication works. Because this has a remember, this has a B module structure. Structure on the left and the right, and they're different. So that's what D has. So in theory, what I can do, I can only do this. I'm taking the x out from the first component. Sorry, so I get y tensor 1, 1. So this is fine, is exactly what I want. But in the second, I want to take the y out. And I have to take it in the other side. And that's what I skipped last time. I skip a step, because I took it in this side. And because I need it in this side. Because remember, we want x, delta x plus y, delta y. So why can I now, so that's the main thing, why can I say, that's what I didn't explain well last time, why can I do this? And then say x delta y plus y delta x. Okay? So I want to explain the question mark. And the reason is simple. The reason is that d mod d squared is an R module, as we said. So we have to think about the action, because here you are really multiplying an element for d times d mod d squared. And the point is that the action that you get is the action induced by the multiplication on the left and on the right. So it's the same action. And that's why when you multiply, if you were multiplying without the bar, you could not commute it. But if you multiply with the bar, you can commute it. And why is the same action? Because how do you get the action here? You get it through the map mu. Because remember, you get it because R is the image through this, is the image of this. So R is RE modulo D, and that's how you get the action. So you get it through the map mu. And now imagine that you send this to mu. This becomes what? It just becomes xy. If I multiply on the other side, it's also xy. So they are the same. Do you understand? And that's why once you go to mu, the order doesn't matter at all because you are in R. So it's because of that. It's written very well in the notes, so you can read it. So I can just write here that d over d square, this explanation of this, is an R module via mu. And that's why this is going to commute. Okay? Okay, so now I want to prove the isomorphism. Okay? And to prove the isomorphism, I just have to show that this guy has the universal property, so that's one way you can do it. Or actually, I can use the universal property to build a map between this, and then show that that map is an isomorphism. And that's the way I'm going to do it. So it's a little different from, you could do it both ways. So if you tried at home, you could do it both ways. So now, by the universal property, remember that this is a universal object, okay? This is the universal object. There exists unique a map phi from omega to d over d square. Okay? So it's a unique R map, R linear map, R homomorphism. So let me call it R homo, but it's an R map that means an R homo. Okay, an homomorphism of R module, such that delta is a factor through D. So delta is phi after D. That's exactly what our theorem says. And so, as I said, instead to prove, if you wanted to do it at home, you could also prove that this has the universal property. That could be possible, and it works. Instead, what I'm going to do is showing that this phi is an isomorphism. Okay? So I'll now show that phi is an isomorphism. So because of this, what do I know? Okay, I know that phi of dx is exactly x tensor 1 minus 1 tensor x. Okay? That's important for us. And now, so the claim is that phi so defined is an isomorphism. And this will finish, actually, the claim. Okay, so we are going to build an inverse of phi. And that's what I'm going to do. And let's do this construction. You have done it maybe to create a canonical module, to make something Gorestan. And you may have done it before when you have a canonical module in a ring and you want to make a ring Gorestan. Yes? No, this is an homomorphism of R module all the time.
And that exists. So the property exists, is unique. But when you apply the universal property, you have to assume that there is, in this case, the delta. You're applying to delta to construct a unique.
So this is universal, okay? This is the universal object. Okay? So I have R omega, this is the universal object. I have R that goes, this is a derivation. We just proved that this is a derivation. So it exists a map here that makes everything commutes. Okay? But this is the universal object I'm applying to. And this is D. And this is delta.
So the delta is of R
we have proved that this is an A derivation. This was the proof that this was an A derivation. And because this is an A derivation, this exists. Okay? I'm not sure. Remember, when we did the proof, we did prove that there exists a unique R map here. Okay, or homomorphism. So if we prove that he has an inverse, there will be isomorphism as R modules. Okay. So now, as I said, I consider the ring RS, which is simply the trivial extension. So is R, different people use different symbol, but usually I use this symbol for trivial extension. Okay? And I don't know how many of you are familiar with it. This is just simply as, so this ring as a ring. So let me write. So this is a ring. And how does it look like? So as a abelian group, is simply R direct sum, omega AR. Okay? And now the multiplication we define it this way. So you take, you want to take elements here to define the multiplication. So you take an x is in R, and then you take an element A in omega, and you want to multiply by y, and y is in R, and now B in omega. And remember that omega is just an R module, so I cannot multiply A and B. I can multiply x and y, but not A and B. You do the same when you want to build a Gorester ring and you don't have a Gorester ring. You do the trivial extension of R and the canonical module. I'm sure you have seen this before, this construction. So how do we do? We just multiply the element in R because we can. That's well defined. And now in the second component, as I said, we cannot multiply A and B, but you can multiply A with Y and B with X. And so that's what we do. We do XB plus YA. And obviously this, since this is in a module, is in omega, and this is obviously in R. So this is a well-defined multiplication. Okay? So this is the multiplication we define. And now, so we have this S, and now we consider, sorry, the razor is here. Now we consider two maps out of S. So the first one, actually they go to S. The first one goes from R to S, and the second, again, goes from R to S. And the way we define it is take an element X here, and you send it to X dx. And here instead, you take an element, again, let's call it Y, and we send it to Y0. So here we take the differential, so obviously is in omega. Remember, because the second component is omega, here we just send it to himself. Okay, so it's just embedding. So this is the embedding. Okay? As a ring. And so these are both R homomorphism. Actually, they are maps of A algebra, really, when you have to, because of the way the thing is defined. This is not a ring. So this is, but even as, so this are both maps of A algebras. Okay. This is obviously a ring homomorphism, just embedding. Now, what do you get? And then depends what you define, because remember that most people define ring homomorphism to send one-to-one, then it wouldn't work, okay? So you have to be careful to how you define it. So now, even that would work in this case. It's okay. Now we use the universal property of tensile product. And we just take RE, so we do the tensor over A, and we get our enveloping algebra. and we send it to S. And my map phi is simply the tensor of these two. Okay? So what it's going to do since it's the tensor? You take xy, x tensor y, call it x tensor y, but the same as xy. Okay, so the element here. And where I'm doing it, I just have to do the tensor product. So this element has to go in phi1 of x times phi2 of y. And that's simply xy, because remember how I multiply these two elements. And then you have y dx, because here you have a 0 times x, so you have just y dx. Clear? You just use the multiplication that I defined before. And now we get our inverse this way, because our inverse, phi inverse, is simply this big phi restricted to D. Okay? So you restrict this to D, and then what do you get? You get a map that sends, so let's, instead to go from here to here, this map, I mean, this is not exactly phi inverse. We'll get phi inverse from here going modulo D square. But first you look at this. This is a map that sends an element of D inside here. So you take x tensor 1 minus 1 tensor x. And let's follow what it does. Okay? So where does it go, this element? In theory, it goes to S, but then we'll see exactly what the image is. So this element, I have to send it inside here. So what I'm doing, I have to do the image of x tensor 1 minus the image of 1 tensor x. So it's phi1 of x tensor 1 times phi2 of x tensor 1 minus, and then the same, phi1 of 1 tensor x, phi2 of 1 tensor x. Now maybe you're faster than me. Just apply this rule. You have to multiply, if this is written correctly. Maybe I didn't do it correctly. Yeah. Guys, did I not do it correctly? Yes. So in the first component, remember I have x tensor y. So I should do the product of the two guys, and you get x squared. Okay? Then I get y dx, and this gives me just, in the second component, I just get x. I have a y. So the x is 0 because, no, the x is 1, and y is 1, so I get 1. So I get just 1 in the second component, minus, and now I have to do, guys, 1. Is it wrong? Sorry?
Second component is 1 times the x.
1 times the x. Perfect. Thank you. And then in the first component, I have the other component. Maybe I did make a mistake, but it doesn't matter. I get an 1. I think I made a mistake, but it's OK. And then, because it's the product of the two, and then I'd have to do the product of x and the derivative, and that's 0. Isn't it? But something is wrong, because it shouldn't be like that. I should get 0 dx. Maybe I apply phi directly. Yes, because this doesn't work. So guys, I don't know what I did, but it doesn't work. Let's try to apply phi directly. OK, help me apply phi directly. So if I apply phi directly, so I'm restricting it to there. So I apply phi directly, but if I apply phi directly to this guy, oh, I made a mistake, guys. That's what I did. Yeah, I made a mistake. Sorry, I should have done phi1 of x and phi1 of y. Why did I do that? OK, sorry. So I'll rewrite what I did wrong. Sorry, guys. I should have done phi1 of x times phi2 of 1 minus, and now it's OK, phi1 of 1, phi2 of x. Now you're OK. OK? That's the problem. That's the whole problem. I made a mistake, because you always do the phi of, this is just acted to R. Sorry. And now you can see I do it in front of you. And now if you use this, you just get x, OK? And remember, for the second one, you have to take y times the x. So is dx. So this is the first minus, and now apply the second, okay? And here, you have to do the derivative, okay, of x. So in the first component, you just get the product, which is x. And in the second, instead, you would have to do the derivative of 1, which is 0. So you get just 0, okay? And now, x minus x is 0, and you get 0 dx. And that's what you want, because you want to go back. So you can see that this map really has an image only on omega and goes exactly back to dx. And now if you go modulo d square, this gives you the inverse. Okay, sorry. I think that way you really understood it. Now I'm going to go to some property. I want to actually go quicker, otherwise I really don't cover anything. Some property of omega, of the differential. And the first property is the fact that it localizes. And you actually have done it as homework. Did you do it yesterday? Did you get there? Okay, that's good. So you know the statement. I'll just put up the statement because it's important, but you have done it already. So it just says, this is localization. So what does it say? Simply that if you have an R algebra, R is an A algebra, like always we have, and you want a multiplicative closed set subset of R, okay? And you take your derivation, the universal derivation, and then the modulo differential, okay, you want to localize the modulo differential at W, and what's happened is that exactly what you would like that happen. The localization commutes, okay? And as I said, you proved this fact yesterday in the homework, so, you know, I skipped the proof or even the check of the proof because you did it. And now I want to go to actually a description using this fact, a description of the modulo differential, so the second in terms of generator relation. And I'll write this in the precise case in which you have a finite, you know, and R is a finite extension, essentially a finite type over A. So, which means that after localization, you know, you just have a, you know, a polynomial ring, infinitely many variable, divided an ideal, which is finitely generated, obviously, because an ideal of polynomial ring infinitely many variable, okay? And then you localize. That just means what R is. You may localize or not, but that's what R is. So R, I can even write it without A of x1, xn, localize at W over the ideal, let's say, f1, fm, okay? So this would be a ring. And then in this case, we just can use our formula, that the proof we did last time. And what's happened with the proof that we did last time? How does the modulo differential looks like? So let's see, and then we can write something nice. Then, because it localizes, you can just localize, okay? And then this is simply the sum of R, the dxi, and now I have exactly n, so I can write here. So this is in top. What I have to do in the bottom, I have to divide, I have to still go modulo the image of the f, the derivative of the f. I went modulo the f, but I have to go to the d of I, okay? Yes?
You wanted me to remind you that fraction.
Yes, even last time, the direct sum was on top, okay? Be very careful. The direct sum was on top, even last time. So here you can see it because I'm really applying as it should be. And then on the bottom, I have to go modulo the differential of these guys. And you remember what the differential are. So for each guy, the differential seems the partial derivative of f, and now you have as many partial derivatives. So I have fj, you know, for each fj, I have this. The partial derivative, you have as many as x's, xi, dxi, and I goes from 1 to n, okay, because this f is in this variable. How many of them? J goes from 1 to m. Okay? And this is what you go modulo for. Okay? And now we can write it even better because I just have to go modulo the generator, you remember? That's enough, the ideal generated by. So I can consider a matrix, I'll call it the theta matrix, which is the matrix, this is with bar because you are in R. So you can do the differential back in the polynomial ring, but then you do it in R. So you can look at this matrix. This is a matrix, and I goes from 1 to n, and j goes from 1 to m. Okay? And then you take the bar. You may have seen this matrix before. This matrix is called the Jacobian matrix. Okay? And what we do is this theorem tells us that you can present the modulo of differential with this matrix. So it gives you a presentation matrix. So it's finitely presented, and it tells you that omega is simply, and this is going to be very important, because we'll consider that case many, many times, when it's essentially a finite type in the future. So you always have to think about the modulo differential that way, is the best way. So you get that you get Rm, and then R dx1 direct sum R dxn goes to omega. And here you have the transport of that matrix. So you look exactly what I go modulo. Okay? So this is called the Jacobian matrix, this one. And remember that the bar just means images in R. So maybe I shouldn't put the images. No, let me do it like this so I don't put the figure. But there, the bar means images in R. Because obviously you can do the derivative up in the polynomial ring, and then you can look at the image. Okay, so this is how we want to think of the modulo differential. And this is very concrete. Okay? It's always useful to have a presentation matrix. Now, I want to show you how and so this is really where the second lecture starts. Actually, it was supposed to start even later, but it's okay. So you had the notes up to here, I think. And now we start the second lecture. And the first thing I want to show you is what we talked last time a little bit, is that the association, you see A goes to R, and obviously you have, which is phi, and then from R you go to this modulo differential with D, with the universal derivation. This association that you can always do when you have R as an A algebra is actually functorial. So what does this mean? So let me write it in terms of commutative diagram, and then we'll get useful exact sequences. So suppose that you have a ring A and a ring B, and you have R, and R is an A algebra, and T is a B algebra. Okay? So you have this situation. And I have a map here, let's call it phi, from R to T. Okay? And let's assume that this is commutative. All right? Then I can, obviously, like I did before, to this one I can associate R that goes to omega A of R. And now let's not call it D, otherwise you get confused. Okay? Then I still have my phi here and T, and here I can put the modulo of differential over R, over B of T. I have this association. And now we ask, is there a map here that makes the diagram commute? And that's what functorial means. And why does such a map exist? I'm going to write it similar to this since it's related to this. I'm going to call it script phi, okay? And this map exists because, why? But think about it. It's exactly the theorem I gave you before. You compose these two, and then you get a derivation from R to T, and you can compose this so it's the basis in A also, because if you fix B, it fixes A, okay? So you have a derivation, okay, a derivation, but this is the universal derivation. So you have automatically, by the universal theorem, by the theorem, you have, you know, a map from here to here. Okay? It's always this universal theorem that does everything. And remember that important remark that I told you, how to get new derivation from old one. You can compose these two, and this gives you a derivation. Okay? A derivation, but that derivation fixes A, because it's a derivation over R. Okay? And so it's an A derivation, and then it has to commute through the universal one. Okay, and now, so this commutes. So in particular, okay, this tells me that the script phi, okay, compose with the derivation from R to A, apply to any R, that's what it tells me, is exactly the derivation of TB applied to the old phi, this normal phi, of R. Okay? Take an element of R, you send it here. So this is what this tells us. I hope you distinguish the different phi. Okay? Not only we have this map, which is going to be very important, this is a T module. I want to make this as a T module. How can I make something a T module? Just tensor over R with T. Remember that T is an R module. So I can make this. This is an R module. And then I can send this map, induces a map here. And how it's going to work? But simply, you take an element T here, okay, and you take an element here, any element, I can call it, I don't know, A. And then, you should remember because it's a module, that's why I don't want to call it. And then it's just a product. You take T, and A is going to go inside with the phi. So the script phi of A is inside here. Okay? So you get a map, a well-defined map this way. And so this is a T linear map. So it's a T homomorphism. It's a T linear map from these two T modules. Okay? And now we are ready to define. Now that we have all this in this blackboard, we are, yes?
Is the top map unique?
Oh, yes, it's the usual thing. It has to be unique. It's unique. So let me write this. It's good to remind us. It's unique, okay? Yes?
Will you define the function balance?
Yes.
Which phi is the upper one? Yes, the function one, right?
So you have an element in T, an element in A, and then here is just a multiplication inside here because this is a T module, so you can multiply by an element in T, and phi of C of A is really an element in this module. So we say an element in this module can be multiplied by an element in T because this is a T module.
The curving.
So this is the curling, sure, is the new psi. Maybe I should do it in yellow. You know, that's much better than curl or not curl because it's not clear. Let me do it in yellow. So that's the unique one. Unique, and then this is the yellow one, and this is the yellow one. Okay? So it's clear. Okay, guys, now I want to come to something which is quite important, which is called the relative cotangent sequence. And to describe the relative cotangent sequence, I'm really going to just use this diagram, but to a particular case if you want, to this case, and we'll see which diagram we get. So if I make it with diagram, it's going to be clear. So the diagram are like this. I take 3 rings, A that goes inside B that goes inside R. So now there is not T, there is A, B, R. So it's easy to say what T is in each case. And then I can look A, and then A can go inside B, and A can go inside R. So here I have the, this is my old R and this is my old T in this diagram. Okay? And the new diagram, I can put A here and B here, and then I can just put R here and the quality here. So these are my old A, B, and here this is my old R and this is my old T. Okay? So now just apply these 2 maps and you get 2 maps. Which map do I get? But if I apply this one, remember in that diagram, T is R. So you get R, tensor, so don't get confused, but T is old R. So let me write there. But this guy is the old T. So you remember, okay? And this is the old B. So if you do that, you get R, tensor, over B, because this is the old R. Thank you very much who is trying to help me. This is so good not to get confused. And then omega, A was the same, so it's still omega A, but there is an R, and R is B. Okay? So we are all at that point, and this goes in who? In omega of A, because the old B was A, so omega A of R. Clear? So this is the one that this gives me. Everybody's there? Okay. Now let's look at the other one we get from the other diagram, because we wrote another diagram. I'll use the orange now to be clear on what the letter means. A and B are the same A and B. Here the only difference is that this is the T. Okay? So what does this give me? It gives me a map from omega AR to where? This should be omega B of T, but B is B, but T is R. So is omega B of R. Clear for everybody? So I got this from this, and this from this. All right? And now, this is the same guy. So why don't we put them together? And that's called the conormal sequence, and says exactly this, that this sequence, R tensor over A over B, I think it is, yes. I don't make a mistake, of omega AR that goes in omega BR goes to 0. And this is ABR. So, is exact. Now, you have to be careful why. I do have well-defined map. This is even a nuke map, and these are well-defined map. But I have to prove that they glue together this way, and this is exact. But this is surjective, and indeed this works. So I have to prove that. Okay? But understand, at least you understand how it come up. Now, think of it, if to remember the sequence, which is very important, remember that in a certain sense, it's almost, some people call it, I call it as Vollmer called it. He always called it a relative cotangent sequence. He was my advisor, so I learned it from him, so that's how I always call it. But Bernoulli often call it change of basis, because it says you're really changing the basis from B to A, and this tells you what you have to pay. So you can remember either as relative cotangent sequence or change of base ring, whatever you want. But this sequence is very important, and we'll see how we do it also applied to get another important sequence after. And let me prove it. The proof actually is not difficult.
Can you pause for just like 10 seconds?
As much as you want.
Thank you.
I told you I speak too fast, and I go too fast. All my life, everything. So until I sleep for 9 hours, because the battery go off. It's not easy. It's not easy, but it's possible. There are obviously, but it's not easy. Yeah. And there are cases in which it's done, and we'll see after when we apply, and you see it's a very interesting actually problem after. Yeah. So actually the proof is a trick because I'm gonna give it mostly as exercise. So it's a real trick. Think about it. I just need to prove that this guy is this modulo the image. And I'm done, it's exact. Since the maps are already there, that's all I have to prove. So, claim. Sorry?
The ABR sequence is exact.
The sequence is A goes to B goes to R.
Is it exact?
No. It's just maps. That's all I ask. I have homomorphism of ring from A to B and B to R. That's it. You could even put them separately, A to B and then B to R. These are just homomorphisms of rings, ring homomorphism, okay? So B is an A algebra, R is a B algebra, but then I can compose the map, that's why I put it here, and R is an A algebra, because it's a B algebra and B is an A algebra, okay? That's it, through the composition. Is this clear so far? Okay, so let's see that the claim. The claim is simply, and that will prove it, that this guy is isomorphic, okay, to omega AR modulo what? R d phi of B. Let me write it better. dr over A of phi B, where phi is this map. Okay? So let's see that, and this map, so I want to show this, okay? This isomorphism, and then I also want to define a map, let me call it DRB, that goes from R to this object, omega AR modulo R dRA phi B, okay, simply by R that goes to the R bar. Okay, so this goes from R to the R bar. Remember, R dr would be the derivation that, D, let's call it D the derivation, this one. So let's call DRAD, because then otherwise I have to put a DRA here too. Okay, and this is D. Let me call it like this. So D is the derivation DRA. And phi is this map. So first let me tell you why this is so what is the claim? The claim is that this module, this one, with this map is the universal module of differential. So how are you going to prove that? And then I'll tell you why is enough. Why are you going to prove that? What do you use? The usual theorem. Okay? You prove that this module together with this map satisfy the universal property. And then you are done. So if you prove that this pair satisfy the universal property, you are going to be done. So the claim is that these are isomorphic, and you prove it showing that this satisfies the universal property. And that you can do at home, and now I'll tell you why this is enough. So how do you prove it? Show that the pair omega AR over R d phi B, okay, this is correct, and then comma, I already call it DRB, I should call it D bar maybe, because I don't know that it's DRB yet, but that's what I want to prove, that DRB is this. That, so I have to, the claim is this isomorphism and this equality. So D bar is the universal module of differential. So that this show that this satisfies the universal property. if you do that, if you show that it satisfies the universal property, automatically this must be this, and that must be DRB. And why does this finish? Because look at this guy. This is exactly what you get here. Because this is omega, and what's the image of this inside here? So that's what you have to understand, what the image inside of this is. And the image, for the way it was defined, is exactly R d phi b. Look at here. That's the image. It was this psi, but this psi was d phi. Remember that this psi was exactly d phi. Phi is the map there, but here we call phi. Okay? Is this clear for everybody? This is the psi. This guy is your yellow psi. Okay? Because of this. All right? And that's what you have to do. Because you have to take D of the map and apply to there. So this is psi of D. So actually it's better if I write this is psi of D of B. And that's exactly what you have to do when you do this. You apply first just the product of R, remember, of T, times the image of this guy. Clear to everybody? Okay. So now we are done with this, and as a corollary of the cotangent sequence, you get immediately this, that if you have, again, now let's call it phi this map, the usual map from A to R, that make R and A algebra, and inside, let me put it here, inside A, I have a multiplicative set, and inside R, I have another multiplicative subset. So this V is in A and W is in R. And you assume that phi of V is contained in W. Okay? So that this induces a map here, if you want. Really not a map, because these are not rings, are just subset. So it really induced as a function, because phi of V is contained there. Okay? So now what we want to prove, we claim, and let me write it in yellow, that, so what we know already? We already know that if we take the module of differential of R over A, okay, and if we localize this with W, that we already know, this is isomorphic to if you enter here. It commutes. We already saw that. That's localization. And we already proved it. Now we want to do more. We want to say that this one, and that's really the content, so this is what I'm writing is the content of the theorem, is that this is actually the same as I even localize the base. So omega of V inverse of A, W inverse of R. Okay? So you can even localize the base, and is equal. So you can localize the base, and you localize R, and you just get this guy. Nothing more. Okay, the localization of this. So what is the proof? And these are all natural. So that's also important. They're all natural isomorphisms. So let me write here natural. Natural because they are going to be induced by this map, and this map were unique. You remember, were unique maps, and that's what you have to, that's why it's natural. So let's see what's happened here. How do I get it from this? How could you get it from this? But the point is, this guy that you have here is going to be 0. Okay? In this case, they have to tell you what A is, what B is, and what R is. Otherwise, you don't understand anything. So for the proof really the point is to tell you who are the guys. So A is really V inverse of A. A is A, no, B is A inverse of A. A is A, and R is omega inverse of R. Take this free and apply that. So why don't we do it together, even if it's a silly exercise, because it slows you down and help you. So this is what? So this is the inverse, and localization is just tensoring. So this is the tensoring. And then what happened here? Remember, A is A, and B is V inverse of A. Okay? So I get, let's see if I did it correctly or not. Where I have V inverse. A and V inverse of A. So this is actually what's 0. So I am wrong. It's the other that is an isomorphism. This is 0. Why is this 0? But this is obvious that it's 0, because you are fixing A. So if you fix A and you do the derivative, A are the constant. So this module has to be 0. You have no choice. And now that tells you that the next one are isomorphic, and the next one are, this is W inverse of R, which is exactly the guy in the middle, is isomorphic then to the last one, which is omega over B of R. So which is V inverse of A, W inverse of R, which is exactly what we want to prove. Okay? So these are isomorphic. And the point is that this turns to be 0, because you are fixing the constant. I mean, you are fixing everything, but then you are going to, remember, every element of here is just an element of A divided by somebody, and when you apply the differential, the top goes to 0. I mean, just write, you have the way the differential goes in the localization. You did it in the homework. Okay, so this is clear now. And then from the relative cotangent sequence, we're going to get another sequence, which is going to be called the conormal sequence, which is also as important. So that's what we're going to do now. So these are very important sequences. So we're going to talk about the conormal sequence. How I'm doing as time? Extremely badly, but it's what it is. So, I mean, I prepared for 3 weeks, not 1 week. Conormal sequence. Okay, so what is the conormal sequence? I'm going to get it from the relative cotangent sequence, but maybe became even more important. And why is it called conormal sequence? Because the conormal module is going to be there. So we consider the following map. The map, like here, that we had 3 map. So A goes to R, and so R is my B there, and the new R is going to be T, which is actually R mod I. Okay? So if you want, this map is surjective. So these are the one you have here. So remember the different role now of the letters, just to confuse you. Okay? So now, by the relative cotangent sequence, RCS, relative cotangent sequence. Let's just take the initial. Okay, what do we get right away? We obtain a map, always. And the map is this map here. Remember the different letter. The last guy is T now, because like before. And then I tensor over B, but B is R. And now omega A stays the same, fortunately. Okay, and the last guy is B, which is R. Okay, so I have this guy, and then it goes to omega A of R. But remember that the R now is the T, so it's omega A of T. And remember how this map is defined. It's just given by the multiplication and the way this goes to this, with the psi. Remember? So I take an element here and an element here, which I can always write as a differential. So let me write it as dr. And where does it go? It goes in T, and then the image. But remember that T is an epimorphic image of R. And remember how we can define the modular differential of T in terms of the one of R. Okay? And so this is just dr bar, the image of the differential from this guy to this guy. Okay? So we get this nice sequence. But now this sequence, in theory, okay, has a co-kernel. And what would be the co-kernel in our case? It would be omega, B is R, and T is R of T. And what is this? 0, because you are fixing all R. So you obviously fix T. So it's 0. So this is surjective. Okay, so I have a surjective map. Clear? Okay, so I can erase this, please? Not yet. This was omega R of T. And it's fixed because T, the element of T are R mod I, so obviously. So you get 0 here. I don't have to put this R anymore. And now you could ask, what's the kernel? Like before, somebody asked, what's the kernel? What's the kernel? And the kernel is very important. And the point of the relative cotangent sequence is exactly determining who goes here. And we, unfortunately, don't really determine the kernel. And I'll talk about this much more, but we'll determine something. And then you'll have several exercises in set 4, because they are difficult, about this. The exercise increase in difficulty. So set 4 is the hardest, if you ever get to here, there. So let me see what's happened here. So let's think about the kernel. So the kernel, who could be in the kernel? So to be in the kernel, okay, you have to think about how do I get omega A of T from omega R. This was really the first remark. Remember that T is R mod I. I have omega A of R. How do I get omega T? I told you first a tensor. I want a tensor with T to get it as a T module, remember? But that was not enough, okay? If it was enough, I would be done. This would be exact. But it wasn't enough. I had to go modulo more things to make the diagram commute. Who did I have to go modulo? The image, the DI. Remember the differential of I. That's what is in the kernel. Okay? Because to get the differential, the modulo differential of T, I have to go modulo more. I have to go modulo DI. Okay? Is this clear? So this is exactly who I have to go modulo. So the kernel is generated by the image of the I. The I is obviously, what DI means, the R, this guy. Okay, this is the I. Because it comes from this differential. Okay? Everybody okay so far? Okay. No doubts? Because remember, I had to make diagram commutes, so you are all okay. So it's generated by this kernel. And now, the point is that the image, this image, is also given by this guy. If you look at you put here, and then I'm going to show that this is exact, I over I squared. This is the conormal module. That's why it's called the conormal sequence. So this image is also the image of the map. So that's why I can put them together. That goes from I to I squared, from I over I squared, the conormal module, to this T tensor omega R, and sends, and any element here is called F plus I squared. Okay? And where do I send it? Exactly where you want to send it, where you should send it. You send it to 1 tensor, because you have nothing in T, so you send it to 1 tensor. What do I have? I have F. F is in I, just the F. Okay? This is where you send it. And now you should ask, oh my God, this map that we have to prove is well defined, because this is act y square. Y is well defined. So it's well defined because d of I square is contained in I, di. So when you go, remember because of the Leibniz rule. So when you go tensor with t, you know, things of R moves and they're 0 here. Okay? So it's 0 modulo t. And here the thing of R moves. Yes?
So one thing that I could do is take the differential from R to this omega AR and restrict it to I, and then that morphism try to tensor it with T. Is it the same thing?
Sorry, what do you want to do? You want to go from here?
Yeah, before taking quotients from I to
From I
to omega without tensor.
df and then tensor with t. Yeah, that's how you can induce the map. Because you think about it, that's actually you can induce the map. You go. What it's saying is that consider this map, and that's why you can do it because of di square, and then tensor both sides with t, which is R mod I over R. This gives exactly I mod I square, okay, and this gives exactly that guy. This is t, so that's exactly what I did. I just did it all together. But that's a map. And the reason why you can do that and is well defined is because of this. Okay? So you have to show that the image go in the right place. So I mean, this shows it right away because you are tensor with RY. But that was exactly the content of that. Okay, and now we have to show that this map is T-linear. Okay, because I claim that this map is T-linear. Suppose I could have started with your map and tensoring at T, but if that's easy, let's call it delta, because delta of Rf plus I square is 1 plus, remember how we define it here, is 1 tensor, and then d of Rf. But this in theory has the Leibniz rule, so you would have to do 1 tensor R df plus f dr. But this guy goes to 0 because f is in I. Remember, f is in I. So if I take it through the tensor, it gets to be 0. Okay? So it's equal 0. And so this is exactly 1 tensor R df, which is R, 1 tensor df. And now you're done. Okay? So this is really R delta. Okay? So now, is this clear? I mean, if you want, I don't have space to write, otherwise, unless I read the T, but this 1 tensor df is the image. So this is really R and the image, delta of f plus I square. Okay? So this map is T-linear, and now the claim, so this is a sequence of T module, and the claim, and that's the conormal sequence, the claim is that this sequence is exact. And that's the theorem. Okay? And now it's clear because that's exactly the proof I did. So the proof I gave you already shows exact because I never claim a 0 here. So I just claim that this is in the kernel. Now you could ask, when can I put a 0 here? And that's a very difficult question, okay? And you'll answer, practically the problem is that you have to go modulo torsion, okay? And the torsion of this module is exactly I square, at least in certain circumstances, is I square modulo the symbolic power modulo I square. So, you know, if you know the symbolic power, a maths exercise, you're going to see what you have to put here to make it exact. Okay? And that's exactly, so if I put here instead when I square the symbolic square, in certain, you have to look at actually the assumption, this becomes an exact sequence. Okay? So if I square is equal I symbolic square, this would be exact. But in general, it's not. So, so this is, and it's difficult. It's been, actually, Vasconcelos was very interesting to see when this was exact. So this is a very important problem in general. And now we give a criterion instead for when this is split exact, split injective. And then obviously you get exactness, because you get a map that goes back like this. Okay? So this is, but this is obviously very strong. It's more than what we need. But so this criterion will give us split injectivity. So this is conormal sequence is split exact. And we see what's the condition to have split exact. Split injective, let me say. So you have so not all injective, but split injective. So to do that, I need first a lemma, which I'll prove here, and then we'll prove the theorem that when I get the split injectivity. So maybe actually first I write the theorem, and then I put here the lemma that you'll need. I have always to check the time. So here, this is not long enough. I'll get a long one. Okay. So the T-linear map, delta, remember this was the map here, is split injective, which means you have that inverse and it becomes identity. Okay? So actually, let me write like this. As a left inverse, that's better. As a left inverse, I prefer to write it like this. If and only if, okay, pi from RS square to T, okay, as a right inverse. And this is the natural projection. Okay? Clear? So that's what we claim. That this is a left inverse if and only if this map pi as a right inverse. So before we prove it, I need to do a lemma. And then I can do it. So I go from R to T, an homomorphism of A algebras. And I consider an ideal in T, and this is the important assumption, such that I square is 0. So as an ideal that has the square equal to 0. And then you want to say, this criterion tells you when a linear map is a derivation. So consider the map delta, okay, from R to I. And just assume it's alinear. Okay? Then the theorem says delta is the lemma is an A derivation if and only if, when you compose phi plus delta, so you do the addition of these two maps, is a homomorphism of A algebra. Obviously, this goes from R to T, because I was an ideal, is a homomorphism of A algebras. Okay? And this is very easy, extremely easy. Could have given it as homework. Remember that this is already a linear. You just have to show that it has the Leibniz rule. That's it. And how do you do the Leibniz rule? But you use what you know here. Actually, we see that they are equivalent. So what does it mean that this guy is an homomorphism? It means that if I apply to xy, this is phi of x times phi, let me call it like this, phi of xy plus delta of xy. That's obvious. That's the definition of phi. And now I'm going to use, sorry guys, the fact that this is an homomorphism, tell me that this is phi, okay, plus delta applied to x, times phi plus delta applied to y. That's our, one side. We are going to see that they're equivalent. Okay? And now, I don't know if you can see down there. Can you see down there? So this thing is equal to what? Is phi of x plus delta x, okay, times phi of y plus delta y. So I get phi of x times phi of y plus phi of x delta y plus phi of y delta x plus delta x delta y. Okay? That's what I get. Now this guy is 0, okay? And because I square is 0, that's where we are, you need an assumption. Because I square is 0. So this is our important assumption. Without this, it doesn't work. You need that this is 0. And then you get the quality of these two. And now these are the same. This just tells you if phi is an homomorphism, which you knew. Doesn't tell you anything. So these two are equal. And so this gets that this guy is equal to this guy. And think about what this tells us. So this tells me that delta, let me write it here, delta xy is phi of x delta y plus phi of y delta x. This tells me that this is a derivation, because that's exactly how you multiply. To multiply element of x, you have to apply phi, because x is in R. So you have to send them in T, and then you can multiply them. And that's exactly. So this is exact, tells you that this is a derivation. Okay? Remember, to multiply, the multiplication is defined through phi. The T is an R algebra through phi. Okay? So this does it. Any question about the lemma? Okay, so I can go to prove this. Ah. No, I didn't prove this at all. I just proved this lemma. No, in the statement I have, so I have this T linear, it applies to this, so T is R of I. Remember, T is R of I. I don't have, I square is not 0. That's the first thing I have to do. I have to reduce to I square equals 0, because I want to apply the lemma. Okay? So the first step in the proof is reduce to I square equals 0. How can I reduce to I square equals 0? But I have to show that everything in the conormal sequence spatializes. Okay? Otherwise, I cannot apply this I square equals 0. So I have to go to that case. So let's see how I do it. Remember, this is the map delta, so it's defined there. All right. And now, so what we know is that if I apply my derivation to I square, this is contained in I times omega by the Leibniz rule, okay, by the product rule. I want to go to I square equals 0, so I want to call this ring R over I square. Okay, so let's try to see what's happened. So I have to erase something, but I don't know what to erase. I erase the proof of this. You remember that this is the derivation, and the eraser is somewhere here. One is here. And I just erase this proof to show you how you reduce. And then I'll have to find space to actually make the proof, and I'll have to erase something. Okay. Here I write homomorphism, so you remember. Okay. So here I write how I reduced, and the simple effect is this. I have to look at this one. This is Ri, remember? And I want to, instead of R, I want R over I square, because I want to make I square 0. So I look at this guy, omega A of R over I square. If I prove that this guy is the same as this, I'm done. Because then I can assume I square is 0. And this is isomorphic to what? But this is still R of I, no problem, and tensor over I square. And now use how you compute this. R over I square is a quotient of R. So use the usual thing that tells me how to compute the modulo differential. So this is the modulo of differential of R, modulo, what do I have to go modulo? But I have to go modulo I square and the image of D. So I have to go modulo di square plus I square. Okay? Remember IDS plus SDI. Okay? So this is how I go modulo. But now this guy is containing I, omega. Okay? And this is containing I omega. And here you are tensoring with I omega. So this is isomorphic to omega over I omega. Okay? Which is the same as T tensoring omega. This is omega over I omega. So I can assume I square is 0. Okay? So this I reduced to I square is 0. So I did this. And obviously pi doesn't change. If you assume I square is 0, pi is also the same map. You know, you have no problem because it's a map from R to R of I. It's the projection, the natural projection from R to R of I. You change this with R. Okay, so now I square is 0. Very good. And this is a map from I to this. I need the eraser. I always throw them in the floor. Okay. So we assume I square is 0. And I have to prove this. So I don't know how I have space here. So I square is 0 now. So this is this. Okay? So let's start. The proof, I'm going to get to this at the end. I'm going to start with this pi. And I'm going to write pi from R to T, which is R mod I, as a right inverse, if and only if I just write what it means. It means that there exists a homomorphism, okay, of A algebras, rho, that goes from Ri to R, okay, because this goes from R to Ri to R, such that what has to happen, pi after rho is the identity in R mod I. That's just a definition. And now this is if and only if. Now what can you do? You can compose them the other way around. You can first apply pi and then apply rho. Then you get an homomorphism from R to R. Okay? So this is if and only if there exists an homomorphism of A algebras, and I'll call it tau. That's the composition the other way around, from R to R. Okay? And what does it do? But I goes to 0 because first you apply this and you send I to 0. So tau with which property? Tau of I is 0. That's the first property. And actually, or if you want, you can write tau restrict to I is the 0 map. Same thing. And let me write it that way, but it's the same. And this is very important, you also get that the identity minus tau of R is contained in I. Okay? Just follow the map and that tells you exactly that. The point is that you can also go backwards. I'm not going to spend now time showing to you, just at home, think about it. That you can go this way is easy, but you can also go backwards. Okay, once you have a map with this property, you can split it up, because it factors through because of the kernel. This tells you that it factors through this one. Remember? Use the first homomorphism theorem. Okay? Yes?
Sorry, can you write down on the board how tau and rho and pi relate?
Oh, tau would be first pi and after rho. That's how you would get it. And now, to go backwards, if you have tau, this thing tells you exist rho, because it splits through. Because this tells you by the first homomorphism theorem that tau is in the kernel of tau, so you factor through. Okay? Yeah, that's what this guy is. Is it clear? Okay. Now look what this tells me. It tells me that something is an homomorphism. Okay? A difference is an homomorphism. I want to apply my lemma. And the lemma says that this is a derivation if the sum is an homomorphism. Okay? So this tells me by that lemma, this is the lemma, that there exists a derivation delta from R to I, okay, with delta restrict to I is the identity in I. Why? Because if you add here, let's see right away how you see it. Yes? Yes? So, take this map. This is my delta. This is delta. Delta sends R to I. So delta is a linear map, because both of them are alinear. It's a linear map, sends R to I. Okay. Now I want to show is a derivation. And this tells me is a derivation if and only if you add something is an homomorphism. If you add an homomorphism, add the identity. Add tau if you want. This is an homomorphism. You get the identity, which is an homomorphism. So you're done. Okay? So this gives me this, all right? And it's obvious that this one, if you restrict it to I, you get the identity, because tau of I is 0. So when you apply an I, tau of I is 0, so you just get the identity map. Okay? And now this is equivalent, okay, to the fact, because you have a derivation, now you use the universal property. So by the universal property now, there exists an R linear map that goes from omega to I, okay? That for which this derivation is obtained by universal derivation. So this tells you that I call it phi. Phi after the universal derivation has to give us exactly this derivation. But this derivation on I is the identity, so is F for F in I. Okay? Because this delta on I was the identity map. And now this is if and only if. Guys, this is not easy, so you have to try, it's every step is hard. So we are at this point. Now I can tensor like he did, who proposed before to tensor. He proposed to tensor. I tensor again. I tensor this with T and this with T, like he proposed before. And now you get the inverse. You tensor with t and you tensor with t. Here you get I over I square, you get this module here. So tensor with t, you get, so this is if and only if there is a t linear map. Obviously you have to show also the inverse, which goes t tensor omega AR to I over I square. And now, how is the map defined? It's just gotten by, you take the identity map and you tensor it with this map. That's it. It's the universal property of tensor product. And so this new map phi is defined exactly like it should. You take 1 times the differential of f. This is dr over a, to be precise, and is f plus I squared for every f, because this was giving you back the identity. And this is exactly what it means that delta is an inverse. This is our inverse. Okay? This is delta inverse. Okay, guys. I mean, left inverse, but it's okay. All right, guys. So now I check the time. I have 4 minutes. Oh, my. I won't be able to do anything that I plan to do. I wanted, so I'm always on my, now I am 1, 2, 3, 4 page late. Last time was 2, now I'm 4. It goes at least the same rate. Instead of at 6 pages a day, I do 4. So it's fine. So I'm going to, what I want to compute next is the rank of the modular differential. Okay? So now I'm going to consider fields, just fields. But the beginning is going to be very easy because it's the same proof that you do for vector spaces, for basis of vector spaces. So just let me tell you, since I still have 3 minutes, let me use the time and just tell you what I'm going to then do next time. It'll be in the next lecture, though. So what, like, imagine it like a preview so you can think about it already. So what we do first and what we want to do, so this is really a preview. Preview. So what are we going to talk? We are going to talk about the rank of the modular differential. And what is the main result we want to prove? First of all, let me tell you, to make it simple, otherwise it would be very complicated, I'll assume that the characteristic of 0. And practically, I take this assumption forever. Until now, I didn't assume anything about characteristic, but at this point, I have to. Otherwise, I have to deal with characteristic P and everything changes. Okay? Remember that this tells me that extensions are separable, and that's going to be very important. And what we are going to try to prove, we want to show that if you have, an extension, finitely generated of field, these are two fields. So these are two fields, one containing another. Remember the tower of fields that you did also in Galois theory. Okay? So what we want to prove is that I can look at the modular differential of big K over small k. So this is a big K vector space. And I want to know what the dimension of this vector space is. And we're going to prove that the dimension of this scatter phase is the transcendent degree of K, of big K over little k. And that's a preview. This is really what the theorem is going to say. So obviously, what I have to do first, this is obvious for you. This is a K vector space because it was an R module, so it has a dimension. So the point is, I have to define this. You may not know what transcendent degree is. So I'm going to define this, define a transcendent basis, give the definition of transcendent degree, and then I'm going to prove the theorem. Okay? So that's going to be the first part of next lecture. And then after that, I finally go to the ramification locus. Okay? And I may have time to start the singular locus, but I think not. So which means that lecture 4 will be all about the singular locus. I want to get to the purity theorem. And hopefully lecture 5, I can start the difference, which means I won't prove everything about the difference, but I want you at least to see it. And I'll give you all the lecture. I'm sure that if I have left over 2 lectures for each time, I have 2 pages. I'll have, lots of pages left. But they're very interesting, so hopefully I can try to skip something in the middle, maybe some proof I tell you, read it, and so I can do more things, okay? It also depends on you. If the pace is too slow, I can go faster. If the pace is fine, I can stay at this pace. So, and I can always say, just read the proof there. We can assume that this fact is true, and let's go on, to tell you. Above all, more we go ahead to tell you the final results. So I can explain you what the things we want to, okay? Okay, guys, thank you so much. Jonathan will send the lecture. Every time I finish, the reason I don't send it all ahead is because I never know where I arrive, and also I notice if I have typos. So I always correct my typos and then give it to him, and he always sends it to you, okay? So every time you get the lecture, and at the end you get the whole thing, even if it's not all covered, okay?
Are there any questions for Claudia? All right, if not, let's thank Claudia again.